Welcome everyone to another mini course at Physics Latam. Today we are honored to have Professor Tadashi Takayanagi giving a mini course on new insights on entanglement entropy and spacetime. Tadashi is a professor at the Yukawa Institute of Theoretical Physics in Kyoto University. And after he completed his PhD in Kyoto University in 2002, he worked for 4 years as a postdoc at Harvard University and ICTP. He was an assistant professor at Kyoto University and an assistant professor in Calif IPMU, Tokyo University, before he moved to his current position in 2012. He has been awarded with many prizes. Among them is the Yukawa Kimura Prize in 2011, the Nishinomiya Yukawa Memorial Prize in 2013, the New Horizon Physics Prize in 2014, the Nishina Memorial Prize in 2016, and this year he was awarded with the Dirac Medal. Tadashi's main contribution has been his studies of quantum entanglement by using holography and quantum field theory. In particular, he discovered a holographic formula for entanglement entropy in 2006, which is real. He has contributed to developing new ideas to relate gravitational spacetime and quantum informations from various methods, and thanks to his brilliant ideas has opened new ways to study and understanding black holes and information theory. So we are very happy to have him with us today to teach us about his breakthrough research and current results. Remember to raise your hand if you have any question at any point. Now I'll leave you with Tadashi. Please go ahead.
Okay, Daniel, thank you very much for such a kind introduction for me. And so I'm very, very happy to give a lecture in this physics Latam series. And in this lecture, I'd like to talk about this use of quantum information theory in the context of quantum gravity, especially through the idea of this holographic entanglement and their recent developments. I'd like to explain and then how we can understand some holography and how we understand also this emergence of this gravitational spacetime. So I have 3 lectures. Today is the first one, and I would like to give an outline, main outline, how we can understand emergence of spacetime from quantum entanglement, some quantum information ideas. So yeah, any point, if you have any question, just stop me and ask question. Okay, so I'm starting, so I suppose some very broad audience, and then I'm give some very introductory talk and then go to more details and for experts. Okay, so let me go on. So, but let me start with the introduction. So this is for a really broad audience, but I'm working on string theory, but also in, for example, especially in Japan. So this is the field is a part of the field called particle physics, high energy physics or particle physics, and string theory is inside of that, and holography and this, ADS-CFT and so on is like also in the part of that. So let me ask, what's the particle physics? As you know, this is a study of fundamental particles and forces that constitute matter and radiation. So, so if we say a very simple way, so this is actually, we want to explore the minimum unit of matter. So if you have some matter, a metal or semiconductor or anything, so if you look into, inside microscopically, then you see some atoms. An atom consists of electrons and nucleus. And electron is already, we suppose it to be elementary particle. We cannot divide electron into 2 parts at this current understanding. But the nucleus can divide into many parts. Like so we can pick up some proton or neutron or proton. And if we look closely proton by using some colliders experiments, so you could see some quarks. Proton consists of 3 quarks. And currently we expect this quark is a kind of elementary particles, so we cannot divide them into several parts. But that way we want to somehow, see the microscopic structure and want to find this minimum unit of matter. This is a particle physics. And so through this historical development of this particle physics, we now understand quite a lot of what's happening in nature. So as we know, so there are 4 fundamental forces in nature, basically, and there are 3 forces that look similar. So electromagnetic force, strong interaction, and weak interaction. They are described by so-called gauge theory. So they are described in a unified way by using quantum field theory. This is where, of course, well known. This is written in the text. So the final theory is called, in this context, it's called standard model, and which is really tested against many experiments in a very nice way. So that way, roughly speaking, these three forces we quite well understood. So this is described by Gauge theory. But there is a force, the other force. This is called, of course, this is a gravitational force, Newton's gravitational force. But at the macroscopic level, to describe our universe, how our universe evolves and so on, we have a nice theory, namely Einstein's relativity, general relativity, that describe microscopic theory of this gravitational force. So we can describe space-time as some geometrical object, and because of this geometry, we can have some gravitational force. This is Einstein's general relativity. But of course, we want to understand in then the microscopic theory of gravity, and that is called quantum gravity. But this is still not completely understood. String theory is a very important candidate of this one, but still we cannot solve all problems. So that way, our target is to understand this quantum gravity, but this means that we have to unify all these different forces, forces in gauge theory and gravitational forces. And this is a very important question, especially if we want to understand the origin of the universe. So to understand the creation of the universe, we need a quantum gravity, because the current universe is very, very large. But if we go past, right, as we can understand from observation, so current universe is expanding, but it's very, very large. But if we going to the past, then it actually shrinks, right? And it then shrinks to zero size. And from this very zero size universe, there is a big bang, like explosion, and that gives the explosion, and that gives a current very large universe. And so the starting point of creation universe, namely this big bang, is to understand this big bang small universe, we have to understand this microscopic theory of gravity. So it's completely different from Einstein's general relativity. We cannot use that, so we need to explore some microscopic theory of gravity, namely quantum gravity. So this is a goal of this kind of our research direction. And but to better understand such a microscopic universe, we want to magnify the universe, right? We need some nice microscope, right? Usually we use microscope to magnify. So, and let's assume we have a very nice microscope, then next question is that what is the minimum unit of space-time? So as I mentioned, particle physics think about the minimal unit of matter, but what about minimal unit of space-time? This is the main question of this, also related to my lecture series. So then I'd like to introduce the idea of holography. I will discuss this much details in much later, a little bit later in this talk, but I'd like to here introduce holography as a nice microscope of this quantum gravity. So we use usually in condensed matter theory, biology, chemistry, we use optical or electronic microscope to magnify cells and spins and electrons and so on. And in high energy physics in general, we use something called accelerators, which is very, very large equipment. And it's sort of, but which plays the same role as microscopes to magnify, for example, nucleus and to see quarks and so on. So we can see some elementary particles or atomic nucleus. So this is a much larger system, but if we want to think quantum gravity is very difficult to do real experiment, though there are many efforts, and maybe in future we have a more, realistic experimental devices. But currently it looks very difficult to do experiments. But we can do some sort of experiment. We can think just in our brain, so we can just talk about we can assume this kind of setup and what happened, and so this is sort of experiment. If we put some black hole and put some object into the black hole, and what happens, and this is a sort of experiment. For that sort of experiment, there is a nice microscope. This is holographic principle. Well, this is called holography, or gauge gravity duality, or special case, this is called ADS-CFT correspondence. So if we use this holographic principle, as I will explain later, so we can magnify some universe, including black holes or other space-time, and then what we see in the end is quantum information. So quantum information is microscopic information, and especially the property called quantum entanglement. Quantum entanglement means some quantum correlation between two body systems that plays a role, and that plays some sort of minimum unit of space-time. If there is some entanglement, there is a universe, and if a lot of entanglement, there is a big universe. Roughly speaking, that kind of structure we can find after we think this. Okay, so this is just an introduction. So now I'd like to go to main part. First, I'll explain, because in this talk, this is of course aimed to understand quantum gravity and gravitational theory, but starting point is quantum information theory. So the idea is to use quantum information theory to understand gravity. So I would like to give some brief introduction of basic concept of quantum entanglement, which is a basic, very important concept in quantum information theory, and then go to black hole and entropy, and go to holography and entanglement. It's connection between holography and quantum entanglement. This is the main part of today's talk. And I would like to also discuss some application of this idea in the context of black hole information problem, and also to understand some emergence of universe from quantum information. Okay, so let me go on. So quantum entanglement, this is also, aimed at a very broad audience, right? So this is a basics of quantum mechanics. So in quantum, basic idea of quantum mechanics comes from this wave-particle duality. For example, we can ask what's the nature of light? So this is a historical question. And then, for example, Newton says that light is a particle because it travels in a straightforward way. It looks like particle, and indeed it's called photon. Photon is a name of particle which describes some light. But on the other hand, it behaves like a waves, like Hoy-Hens and many other researchers thought about. And this is because it shows diffraction and interference, right? If you have some laser beam and laser pointer, so you can easily see this kind of interference picture. Very easy to make it. And actually, as Einstein, roughly speaking, almost 100 years ago, as Einstein claimed, so both are correct. Both ideas are correct. And but this is also true for not only light, but also any particles, any matters, like electrons and other matters. Any matter, such as electron, also have this wave-particle duality. So this is our origin of quantum mechanics, idea of quantum mechanics. So quantum theory is based on this wave-particle duality. Particle is equal to wave. And as you know, like in quantum mechanics, we use wave function to describe a state of some quantum system. So, but this means that this wave means very important thing, like we can superpose, right? So quantum state, we usually this bracket notation. So this psi, it can be linear combination of two different quantum states. And so this is because this is a state is now particle can be represented as a wave. Wave is just function. Right? You can take some linear combination function, so we can superpose different states. This red state and green state, we can just mixture as much as you like. So this is a very important point of quantum theory, and this is actually leads to the idea of quantum entanglement, as I explained. So now I'd like to introduce the idea for the qubit. So we know some classical bit, right? Classical bit is 0 or 1, right? These computers right? Uses this classical bit to restore some information and also do some operation like calculation and so on. Maybe 0 means lower voltage, low voltage, and high voltage is 1, like just this kind of very simple two different states. And if we go to quantum mechanics, actually, as we mentioned, we can take a superposition of two different states. For example, in quantum mechanics, the one nice example of bit is electron spin. Right? Electron is 1/2 spin. That means up spin or down spin, or right rotation or left rotation. And we usually call right rotation as a 0 state, and left rotation is 1. This 0 and 1 is a binary. Bit. Sort of bit, but the difference between this, different point in this quantum case, as opposed to classical case, is that we can take a linear combination. We can take A times 0 state plus B times 1 state, right? Left rotation, right rotation. We can mix these two different states as much as you like. So this is like, basic unit of quantum state. This is called qubit. And this is, in the end, this is identified as the minimum unit of space-time by using these holographic ideas. So anyway, this is called qubit, and this is a basic unit of data in the quantum computers. So that means, we can, so you can think this is like this up and down, just one up or down. But you can imagine this qubit as some rotating arrows. Right? It has a huge information, even though just one qubit incorporates a lot of information like this. And quantum computer operates them and to do some calculation. And very nice. And point out, we can take a superposition. Now the superposition helps quantum computer to do many calculations at the same time, right, in a parallel way, as compared with classical. Okay, so now we go to quantum entanglement. Now we are prepared to explain quantum entanglement. But only non-trivial thing is that we need to prepare not only one qubit, but two qubits, at least two or three, or more than two quantum systems. So let's assume A is a one qubit and B is the other qubit. In my talk, I'm always talk about A and B. A and B are two-body system, and A can include many number of qubits, and B can include many number of qubits, but they are correlated. So but here it's very simple case, just A is just one qubit and B is one qubit. Then, for example, we can think about this kind of quantum state. This is one of the states called Bell states. So if A is 0, then B equals 1, B is 1. But A is 1, then B is 0. So that way, even though if we just look at A, right? If we see A, it can be 0 or 1, both are possible. But if we know the result of A, if we measure A, and if we know the result, it's just opposite, right? Guys appears as a B, right? If A is 0, then always B is 1. So that way, information of A and information B are highly correlated. This quantum correlation, this only happens in quantum correlation because we take this superposition, right? This is only true in quantum mechanics. This is called quantum entanglement. This correlation between A and B is called quantum entanglement. In other words, though we know the state of the total system, this total system, so what's the total system? We can just answer, this is the total state. This is a very sharp answer. But if we just talk about the state of A, it can be 0 or 1. So that is a bit ambiguous. This is a very special nature. In classical system, if we know all systems, then that means we also know each subsystem, small systems. But in quantum mechanics, even though we know total system, if we look at the subsystem, smaller system, there are ambiguity of information. This is a very special nature of quantum entanglement on the quantum side. So this is we will heavily use this property later. Okay. So, but this is a very heuristic idea, maybe intuitive idea or qualitative idea. But we can, in physics, we always need some quantity which quantify such a phenomena or property. So this is a, entanglement entropy. So this is a measure of amount of quantum entanglement. So this is the main quantity which we will work with. And this is related to the size of space-time, more precisely area of space-time. So this is a entanglement entropy, and I just sometimes just called EE. So that let's first I give some very heuristic definition and then go to more precise definition. So entanglement entropy between A and B is actually the number of Bell states, Bell pairs. This is called Bell state, or it's a pair, so it's a Bell pair. It's called number of Bell states between A and B. So let's assume A consists of 4 qubits, B consists of 6 qubits, and let's assume there are 2 such a Bell states. Right? This guy and this guy is correlated, this guy and this guy, other guys are completely independent. So that case, we call entropy is just 2, right? Because there are 2 Bell states. And in other words, if we think from the viewpoint of observer in A, so A only can see A, and the observer cannot see B, cannot be accessible to B. So then, the amount of lost information if observer can only accessible to A. So this is actually also at the same time this entanglement entropy computes. So if observer cannot see B, then how much information is lost? For example, these guys, right? If observer can all part of A, then these guys are completely independent from B. So we can this observer can completely know these two guys. But this guy is correlated to B. So even though we can measure this one, but it's not, that means that miss some information. So this is a point of this entanglement engine. So their information is correlated to each other. Okay, so this is a heuristic explanation, but more precisely, in actual calculation, we do the following thing. But these two are actually equivalent. So to precise definition, to define entanglement precisely, so we factorize Hilbert space. Of course, this A and B, like this A and B, their Hilbert space is factorized. In this case, 5 qubits and 3 qubits. But it's just factorized. This is a starting point. And then in quantum mechanics, we have some quantum state, right, which describe total wave function, which describe AB system. And then we introduce reduced density matrix. This is a density matrix which is obtained by tracing out B. We trace out. So observer is only can be accessible to A. Observer cannot probe B. So we trace out. So this density matrix rho A is the observer. So, and then we calculate this entanglement entropy by this famous formula. This is a famous von Neumann entropy formula, minus rho log rho. Rho is a probability distribution, so it's like always less than 1. This is always positive. Log rho is negative, so we need a minus sign. And this is an equally derived probability distribution. This is called Shannon's entropy. It is classical information, classical entropy of information. But this is a quantum version of it. And a very important theorem, which you can learn from textbook in quantum information theory. This looks, mathematically beautiful, but it's not, maybe not so physical interpretation, maybe not so much immediately, but there is a very famous theorem that I'm not going to talk about this but, in this talk, but there is it is possible to show this is just equal to the number of Bell pairs, which we can extract from AB system. So this ideal case is this one. Right? We just count the number of 2. Right? And this, if we calculate this, you can just get 2. But in more general, it's more complicated. This guy is entangled. This guy also has a similar entangled. This guy is very, very complicated. But in that case, we can simplify the system by something. We can act some local operation A and B, unitary transformation, projection measurement A and B, and some classical communication. That is only classical interaction between A and B. Then you can get some very simple system like this, and then just count the number of Bell pairs, and that precisely agree with this formula. Okay, there is a question. Is it true that yes, that's right. Okay, good question. So SA equals if total system is pure state, always you can show SA equals SB. Yes, that's the reason. So I'm already talk about SA, but didn't talk about SB. But they are same thing. This is equal to SB. But if the total system is a mixed state, it's not true. Canonical and this is not true. So, but that case, we lose this quantum information theoretical understanding. But that's fine. But still, physically, it's sometimes useful. But here, I'm assuming everything is like pure state. Okay, good. So now I go to some example. So I said that this gives a number of Bell pairs, and this is true. So we can think about this as a very trivial example. This is like a fact. This is just a direct product state, right? Even though this is a linear combination, but this is direct product. A and B completely independent, no entanglement at all. And if we trace out B, then you get this one. And you can diagonalize just 1, 0 matrix. Eigenvalue is 1, eigenvalue is 1, but other eigenvalue is just 0. So that means entropy is 0. And a similar way, you can do, okay. So similarly, you can do this, do the same thing for this Bell pair state. And this is an entangled Bell pair or Bell state, or this is also called EPR state, Einstein-Podolsky-Rosen. They are equivalent. EPR state, they are entangled. And indeed, if we trace out, we get 1/2 eigenvalue. So then you get a log 2. Right? Log 2. And so log 2 is a 1, means 1 entangled. If we put the base is 2, then it's just 1. Right? If 2 of such a guy, then you get a 2. SA equal 2, right? Like this. Like this. Okay. So this is a basic example. So, question, what's the meaning of pure states? Okay, physics, okay. Pure state and mixed state. So maybe let me write it here. This is very important. Pure state is just described by wave function. So if density matrix is written by just single state, this is the, in other words, if we, in terms of matrix language 0, 1, 0, 0, 0, that means really pure. Only one state appears. But the mixed state is like this. This is like, for example, canonical ensemble, beta H, right? Or maybe it's like many different eigenvalues appears, right? This case is many different quantum states are mixed. So that is called, this is a mixed state. This is a mixed state. This is a pure state, okay? And quantum information theory, so I mean more precisely, so in quantum information theory, entanglement entropy measures quantum entanglement only if we think pure state. Total system is pure, this AB system is pure, then entanglement entropy measures the quantum entanglement. If we do for mixed state, then it's not good to measure. But still, physically, sometimes useful. So sometimes I'm use that as I will explain it. Okay. Now, so and this is the entanglement entropy. So, but maybe you might think entanglement entropy is very complicated. I mean, mathematically good, but maybe not good for real physics like measurement and so on. But nowadays, it is true. It's the measurement of entanglement entropy is quite hard. But nevertheless, nowadays, owing to some developments in condensed matter physics experiments, so now we can measure entanglement. These are some examples. These two. These are ultra cold atoms. This is changing some interaction. This is like a Hubbard model, but it's changing some repulsive force. Then entanglement entropy changes, enhances when repulsive forces get small, right? It's more, this is more confined. Repulsive force is very large, but it's like this. And also trapped ion simulator. So they can measure this, realize this kind of spin model and follow time evolution. Under time evolution, entanglement entropy grows, like usual second law of thermodynamics. It grows, so they can measure this growth of entanglement. Okay, so anyway, these are entanglement entropy. Okay, so now I'd like to, switch the topic, but in then they are, describe the same thing. Interestingly, this is a very important point of holographic idea. But here I'd like to talk about now macroscopic. Entanglement and so on looks like true for very microscopic quantum system, but now I go to much larger system, namely cosmological system or black holes. That's what I'd like to talk about. Okay, so entanglement, there is a question, is not monotonic. I don't know the meaning of monotonicity, but it's actually, for example, something, what I said is LOCC, like entanglement distillation. If we want to distill entanglement, it's always entanglement entropy decreasing under LOCC. There are many monotonicities faults. Okay, so okay, so I'm talking about black hole. So black hole is, as you know, like I think probably this is the main topic of this school, but it is extreme dense astronomical object. But because of a very strong gravitational force in Einstein relativity, so if you have a massive particle, massive object, then we get a curved spacetime. So and because of curved spacetime, we have non-trivial potential, and if you have additional particles, they gets closer to this massive particle because of gravitational interaction. Comes from this geometry. And but if we have a very large massive object, then to make a hole, right? It's just completely gone. And so that is a black hole, and this is a characteristic object in Einstein's general relativity. So there is the area, the region called black hole is surrounded by horizon, especially event horizon, and even light rays cannot come out of that because of very strong gravitational force. And okay, so the important concept is black hole entropy. So you can imagine, so there are many ways to make a black hole. Now there's many black holes are really observed in the universe. But one way to make a black hole is to think of a very compact, very heavy, very dense star. They have some gravitational collapse and make a black hole. So originally it was a star. So it looks like, I mean, outside observer can see inside the star, right? So how many particles are there, and so what kind of color it is, and so a lot of information can be observed by some observer. But once we have some gravitational collapse and it becomes black hole, then outside observer cannot see inside the black hole, so cannot extract information. But this itself is not any problem. This is not the problem. And originally, a lot of information just hidden inside the black hole. But this suggests that inside the black hole is something very unusual object, and it seems to kind of store or hide a lot of information. And this amount of information, we call it black hole entropy. Anything we cannot probe is like called entropy. This is also true of thermodynamic entropy. So some microscopic degree, which we observer cannot see details. So that is the entropy. So we call this black hole entropy. But for black hole entropy, it's very surprisingly. So this is very beautiful formula has been known more than 50 years, right? Since this Bekenstein-Hawking formula. So it is a bit surprising also to me that this formula was already discovered at so early time, even though it includes a lot of ingredient of quantum gravity. So, and still I should say this formula itself is still mysterious. And always this is a key to explore more about quantum gravity. So even though we know holography and so on, I don't think we can really say that we completely understand this formula. So it's, and also this formula is very fascinating because it takes a very simple form, very beautiful form. So black hole entropy is essentially proportional to area of black hole, right? This area of event horizon. This A black hole is a surface, but it involves a lot of constant, and most importantly, Newton constant, because this is of course gravitational phenomena. It's 4 times Newton constant divided by this, and so Newton constant, but also it involves h bar, Planck constant, and light velocity. This is 4-dimensional case, light velocity, and the Boltzmann constant because this is entropy, and this suggests that so. First of all, it's surface area. This is a very geometrical formula. And the Newton constant means, of course, this gravitational formula. And the Planck constant means this quantum mechanical formula. And finally, Boltzmann constant means statistical mechanics. And also, if we combine quantum mechanics, this is a quantum information is hidden behind this. So that means we have to combine these ideas. These are usually we studied in different textbooks, but we have to combine different textbooks to understand this formula, namely quantum gravity. To understand the quantum gravity, we have to combine these ideas. So this very famous formula tells us that. And at the same time, because this is entropy, black hole looks like some dynamic object. It also has, as Hawking pointed out, it has also temperature, and it radiates and so on. So it follows some dynamics. This is very mysterious. But if we say what's the most mysterious point, is I can raise these 2 points. First one is black hole entropy is proportional to area, is not proportional to volume. Usually in thermodynamics, I mean entropy or energy, free energy, such as extensive things are always proportional to volume, but here it is proportional to area. And the second point, so this formula is already obtained even when we don't know at all quantum gravity. So the entropy is originally, as you can imagine, how statistical mechanics idea is developed. So quantum mechanics is very important. So we need some discrete energy levels, and then we can count number of states, and taking a log of microstates, we get the entropy. This is the idea, microscopic idea. But this is actually, derived without using such a quantum idea. And interesting, this only appears classical theory. So if we think, quantum field theory, but let's think classical scalar field theory or classical fermion theory. You can solve equation motion and so on. You can get also soliton, sine-Gordon model example, but they don't have entropy at all. But if we think spin to particular name gravity or Einstein gravity, even at classical level, we can show it has an entropy. So this is a very special point of gravity. So these two are very special nature of gravity. So, and here we have a very interesting analogy between now we want to combine this idea of black hole to quantum entanglement. So we can actually have a very interesting analogy between black hole and qubits. And this is actually original motivation why people start to think about entanglement entropy in quantum memory system. That's quite early time, 1986 by Bombelli and Sredonic in 1993. This is a really original paper, and the reason they think entanglement entropy in quantum field theory or quantum memory system because they want to understand black hole entropy. So this is because of the following analogy. So in black hole, we have an observer outside, and the observer want to see inside the black hole, but the observer cannot see inside the black hole. So some information is lost inside this. On the other hand, we can also think about the observer in quantum spin system, a lot of spins. And so we can take some region A here and region B here. As previously, we talked about this kind of array, but you can talk about two-dimensional spins. So this green guy is a spin, right? And the Hilbert space is factorized HB and HA, right? And we talk about the entanglement between them. But as I explained that, so entanglement entropy is somehow amount of lost information when observer can see only A but not A. Sorry, not B. So observer cannot accessible to B, then some information is lost, and that is measured by entanglement. Because of this, there are A and B are correlated, so we need also information B. That's the thing. So this two situation, because anyway, observer is only can see A, and observer can only see outside the black hole, looks very similar. And both are entropy, and both measured, roughly speaking, lost information, so they should be same. So these are these people originally thought. So black hole entropy might be equal to entanglement entropy, right, for this system. But this doesn't work out, and this is not so successful. This is because of following reason. This is the immediate truth. But there is a very surprising thing. Both are proportional to area. Black hole entropy is proportional to area, and entanglement entropy in this quantum measurable system is proportional to area because, for example, in A and B, and most strong entanglement are obtained by this border. Right? These two spins are very highly entangled, but this spin and this spin not so much entangled. So main contribution from the border. So both are satisfy area law, but the difference is that this black hole entropy, we already see universal, right? This is universal formula, it's finite, always Newton constant. Once we fix Newton constant, everything finite. But the entanglement entropy, this I didn't explain, but this follows area law, but it always includes UV divergence, or also depends on the number of fields. So it depends on the what kind of, material or scalar field. We can think some scalar field here, and how many scalar. If we have twice number of scalar field, we get the entropy is double. So the formula is not universal. So that way they disagree. So, but to understand this connection, this is a very nice, very heuristically very attractive idea, and to really correct, to get some really correct version of this connection, we have to think about holography. That is the main topic of this lecture. Okay, there is a question. But thermodynamical entropy, sorry, isn't the black hole entropy a thermodynamical entropy instead of von Neumann entropy? So how does the analogy work? Okay, but actually, black hole entropy, so it depends on the setup, but especially in the context of called eternal black hole. Eternal black hole is, okay, so eternal black hole is like, if you are familiar with Penrose diagram, we can write in ADS3, it's like this. ADS picture, it's like this is singularity and this is the horizon. So I'm talking about this kind of black hole. This kind of black hole, this side and this side are really entangled with each other. And that case, it's if you trace out, there is something called theory 1 and theory 2. If we trace out theory 1, then from this side, it looks like thermodynamical. So it's this like entropies become thermodynamics. At the same time, you can regard this thermodynamical entropy as a black hole entropy in terms of entanglement entropy between these two sides. So then it's really also same as von Neumann. So that way, Depending on the situation, but we can, very interesting situation, we can say black hole entropy is really von Neumann. So in that case, still this issue appears. I hope this answers the question. And also there is other question. So entanglement entropy in quantum field is always divergent. However, black hole entropy is finite. Why? Yeah, that's good question. And okay, that is good question. So, I mean, they are simple answer is they are different. So black hole entropy is we don't know, right? We said it might be entanglement entropy. Then so it looks like this area rho. It looks like the area divided by epsilon to some power. Maybe in this case, epsilon is some square, for example, in four-dimensional case square. This case is just first part, but okay. Area, this is the area rho divergence, but the black hole entropy is area divided by Newton constant, or the Newton constant. So these are finite. So they are different. So simple answer, they are different quantities. Looks like different quantities at this stage. So I want to resolve this kind of question problem by using ADS-CFT correspondence. Okay. And to have area rho, the theory must restore. Yes, that's right. So if we talk about just AB system, generic state, highly excited state have a volume law. Entanglement entropy SA is usually proportional to volume law. And only special case, we get the area law. Area is proportional to area. That's the case when interaction is local. And if we, start the quantum field theory is usually local quantum field theory. So if ground state of quantum field theory usually satisfy area because of that. Okay. But actually, yeah, this quantum correction to black hole entropy is related to this entanglement because quantum correction is UV divergent. Looks like this is an additional comment. But if we want to really understand this guy as an entanglement entropy, if we just think about the same spacetime, you have a black hole on outside, and the entanglement this doesn't work. We have to use holography and change the dimension. This is a very important point. Okay, so now I'd like to introduce holography. So this is the holographic black hole entropy formula. Okay, so this is a black hole entropy formula. I erase many constants, but this suggests that this is proportional area. Entropy is a degree of freedom. So degree of freedom of gravity seems to be proportional to area. Okay, so this is a very surprising thing, but Tofu and Saskan think this is a very essential fact. And then we get the following picture. If this is true, then gravity, there is some gravity or some manifold, but actually there is a equivalent, some material system, matter system, which don't include gravity at all. So in terms of quantum matter, it seems to be this matter lives on the lower dimension, one dimension lower. It looks like boundary of this spacetime. So if so, this entropy counting works. Here entropy looks like proportional area in higher dimension, but in lower dimension picture, it's proportional to volume, right? Dimension changes. So they are both consistent with it. So this is a called holographic principle. So if gravitational theory is equivalent to one dimension lower theory, which lives on the boundary of the space-time manifold. This is the hologram. Of course, this is a very heuristic, so we need some concrete example, and indeed, as Martha Xenophon, there is a most well-known example of holography called ADS-CFT correspondence. This was found in the context of string theory, as we'll explain it later. But this is the following duality. So this is a very best-known example of holography, and gauge gravity duality is given argues these two different theories are equivalent. One theory is a gravity on anti-De Sitter space. So D plus 2 dimension. So this is my convention. Maybe if you don't like it, you can call D plus 1 and just erase this one here. D plus 2 dimensional anti-De Sitter space. And anti-De Sitter space is a universe with negative curvature, negative cosmological constant, and the matrix looks like this. And this matrix looks nice in the sense that we have some z direction here. This z is here, right? and it's warped, right? And z equals 0, here it's z equals 0, metric divergent, right? It's very large, it's very large, right? Metric divergent. But if z goes to large, it shrinks to 0 size. And except z, it looks like just Minkowski space, right? Lorentzian flat space. So this is this direction is x, and this direction is t, and this is the x direction, right? So this is a Minkowski space. It's an fibered over this non-trivial direction. This is called extra dimension. The direction. And in area safety, as we'll discuss later, these are I interpret the length scale. So large G means infrared and small g is UV. So this is a UV. Okay, z equals 0 is UV. So we get a UV divergence, and that's the reason metric also diverges. Metric is related to degree of freedom, and degree of freedom gets large in UV system, UV limit. That's the reason we get a UV divergence in quantum field theory. And so yeah, claims that this is anti-Doshita space, and this is equivalent to gauge theory. D plus one dimensional theory, but because of symmetry of anti-Doshita space, this should be conformal field theory. Conformal field theory is a gapless theory. D-dimensional gapless matter to quantum critical point in condensed matter theory, or you can imagine just quantum field theory with only massless fields. And famous example is like supersymmetric, n equal 4 supersymmetric Yang theory, where quantum correct, beta function is not to be punished. So, but anyway, so this is gauge theory don't have any gravity. So this non-gravitational theory is equivalent to some gravitational theory with negative cosmological. This is the area safety correspondence, and this is confirmed by many, maybe 10,000 of paper, confirm this relation, and always we get a, perfect match. So we believe this is true. So this is the area safety correspondence. This is the main framework also I'm going to work with. But here is a very naive sketch. So this actually related to entanglement. So if we think some quantum material, especially conformal field theories include a lot of different scales. So this is a short range correlation. You can think this correlation as entanglement, short range entanglement, and middle scale entanglement, and large scale entanglement. And we take some Fourier decomposition of each entanglement, and the short wavelengths entanglement is just recorded here, and the middle scale and large scale, like just make an array of that. And this is basically this kind of ADS spacetime. So you get just a single state, just one dimension lower seat, but you can decompose, and then you get a one dimension higher, right? Like this way. This is the idea of this safety. Very roughly speaking. But yeah, also at the same time, let me mention that how ADS safety was discovered. So this is then we have to think about the string theory. String theory is the best candidate of, we suppose it's the best candidate of quantum gravity. And string theory start from the idea that, elementary object is usually in particle physics, elementary object is particle, elementary particle. But this doesn't work for gravity. As I mentioned in introduction, if we think this kind of idea, we just talk about quantum field theory. This is elementary particle, theory of elementary particle, but this doesn't work for quantum gravity. We get a UV divergence and so on, many problems. So to improve situation, string theory is introduced, and that's assuming that elementary object is not a particle, not a point particle, but a string, a one-dimensional object. And the one-dimensional string, there is only two types. One is an open string. The endpoints are, there is a two endpoints, like this kind of structure. Another one is like a ring-like structure. This is a closed string, no boundary at all. So there are only two. You can very easily imagine there are only two kinds of strings. And this open string, you can attach some charge at the boundary, the plus charge and minus charge. Then this can describe quantum electromagnetism, or more generally, gauge theory. It's described. So it's like a theory of matter, standard model and so on. But the closed string, actually, there is no charge. And but there is a double degree of freedom. You can send a wave in the left direction and right direction. That means spin. This means spin 2. This is spin 1. So that means this describes gravity. So this describes universal gravitational theory. But the important point is that these two guys are actually equivalent because string is just only one string. You can cut into different angles. So you can think about the cylinder, right? You can think about cylinder and you can cut in the vertically, you get a closed string. But if you cut horizontally, then you get open string, right? There, but this material string itself is the same thing. So closed string and open string they are equivalent. And this actually leads to the idea of ADS safety correspondence. So gravitational space-time here and closed string is propagating, but this closed string can attach at the boundary, and that makes open string. So closed string, you have a closed string, but you can separate this into two open strings. And this open string describes gauge theory. So this is the origin of ADS safety, and more precisely like this. So to make an anti-Doshita space, this is sort of black hole geometry. This is not exactly black hole, it's a more properly called black brane. But to make a black hole, we need a very, very heavy object. In string theory, heavy object is known as one good candidate of heavy object is called D-branes. D-branes is a kind of plates or planes where open string attached to each other. So if there is n different D-branes, each seat, each brane, you can attach open string. So this open string can extend this to this, or this open string this to this, and there are n square different. If there is n D-branes, there are n square different types of open strings. So the n square looks like matrix, right? That's the reason we get a gauge theory. It looks like gluons in QCD. And this theory, because this is a very heavy object, following just general relativity, it back reacts geometry. And in the end, we get the black brane geometry, namely anti-Doshita space. So in this way, then, these branes are now kind of dissolved into background space-time. We can forget about D-brane, then it looks like theory of gravity, right? These two are equivalent. That's the idea of ADS. This is how also Malta-Sena formed this ADS safety correspondence. So, and example, thermodynamics of these materials, some gauge theory, it should be equivalent thermodynamics of black hole. So black hole thermodynamics is very mysterious, but if you use ADS safety, we can just relate it to just very standard thermodynamics, where entropy is proportional to volume here. It's the entropy of proper area, but dimension changes, as I mentioned, they are consistent with each other. Okay. So this is the ADS safety correspondence. And maybe before I go on, I would like to also mention different types of space-time. So we talk about the ADS, anti-Doshita space. This has a negative cosmology constant. But what about other space-time? In ADS, we can have a nice ADS safety correspondence. And so where one dimension changes, right? Dimension changes. So CFT, so this conformal field theory, we write it CFT. Yapres theory, the CFT lives on the boundary. And the bulk is ADS. Right? One dimension is, so from the viewpoint of CFT, this quantum field theory, from quantum field theory, it looks like one-dimensional space direction is emergence. We call it the emergent space. Space direction is emergence, Z direction. This Z. This direction, this Z direction is emergence. So quantum field theory lives on this Minkowski space, but Z direction is emergence. So, and this is the ADS safety correspondence. But what about other space-time, right? Flat space and Doshita space. Flat space is just flat space. And this case, actually, maybe we don't need so much about holography because there are also very interesting holography called celestial holography, also very one of current topic. But also string theory in flat space, we can solve. String theory very well. This is in a textbook. You can see the textbook of string theory. Usually, most of examples are flat space. We can compute scattering amplitude, even taking into account very quantum gravity effect. So in that sense, maybe not urgent. But the most urgent thing, another urgent problem is to understand the holography for Doshita space. I will explain this maybe in my final lecture, third lecture, next week, next Monday, I think. But this is a very tough problem, and but this is quite a hot topic these days, but still not completely understood. It's a really developing subject. And this is difficult because if we think this kind of holographic idea, so emerging, so there is a DSCFT correspondence proposed as Strominger. And this tells us that gravity in D plus two-dimensional Dojita space is equivalent to conformal theory lives on the future infinity. Depending on the coordinate, but it's a future infinity. So this means that here ADS space direction emerges, but time direction is emerging. So this future infinity don't have a time direction. So it looks like quite a Euclidean theory. From a Euclidean theory, somehow time coordinate emerges. This is very difficult to imagine, right? So this is the reason many things complicated, but also you can see this from the viewpoint central charge. This also I will talk about this in my third lecture. But in the ADS case, there is a well-known formula. So in 3D, ADS3 CFT2, that means three-dimensional anti-Josta space is equivalent to two-dimensional conformal theory. And that case, two-dimensional conformal theory is characterized by central charge. This is measured degree of freedom, central charge. This is given by ADS size of ADS. This is called ADS radius. ADS radius is sorry. This one. This is ADS radius. R divided by Newton constant. If ADS size is larger, then central charge is larger, and degree of freedom is CFTs gets larger. This is fine. But in Dojita case, if we do that, actually we get the imaginary value of central charge. So this is very unusual. It looks like very non-unitary CFT appears here. So that way, the Dojita space is very exotic. Okay. Okay. Yes. Also, you can see this from the thermodynamics. ADS has a nice thermodynamics. It looks like entropy and as a function of energy. This is a microcanonical number. So this should not go linear behavior, right? This means that this is the second derivative is negative. This means that specific heat is positive. So it's a nice thermodynamics. But flat space, as you know, Schwarzschild black hole satisfy entropy is for E square, looks like this. This has a negative specific heat because of this higher power. Already thermodynamically unstable. But Dojita space is much more strange, right? It's like going down monotonically degree. This is also very surprising feature. So that way, maybe if we want to try first, then ADS it looks definitely best one. Right? It looks very similar to usual material. So that's the reason ADS CFT is most well understood until. Okay, so but maybe it's good to have some rest. Break. But before that, let me pose one basic question. So if ADS CFT is correct, then we can immediately come up with the following question. This is called also locality question. So we have some CFT here, and it's equivalent to this bulk gravity ADS. And then this whole CFT is equivalent to this region, right? Bulk region. Then, but if we pick up only particular region called A, then this region A might be related to some region, some partial, some sub-region inside anti-Josta space. Is this true? This is a question. So to answer this, actually, so it's not so easy, right? This information related to this one. How can we calculate it? In physics, it's always easy to calculate some quantity. So for that, we want to compute entanglement entropy. So entanglement entropy, as I mentioned, describe some correlation, amount of correlation between A and B, or if observer is here, then some amount of information lost by tracing out this region A. So that means from this observer, entanglement entropy measures amount of information included in this region A. So how we can calculate this entropy? Then probably we can answer also this question, as we will see, discuss later. Okay, so maybe it is just one now, so maybe it's good to have some break, 5 minutes. Thank you. Okay, so let me continue. So this is a question I want to ask, and now I would like to give one answer to this question. This is a holographic entanglement. So this is I will give actually 3 different type of formula. in this lecture, or maybe also including coming lectures. And this is the first one. Can be applicable to static spacetime and static quantum state. This is a formula which I worked with Shinsei Ryu. And so this is a calculation of entanglement entropy by using ADS safety correspondence and assuming static spacetime. This is actually very geometrical. So let me explain. So this is the ADS safety setup as I explained. So boundary, this is a boundary where conformal field theory, CFT lives here. And this is equivalent to gravity in the bulk. And now we consider some region A here. Region A is here, and region B is outside. And then we want to calculate the entanglement entropy for A. And for that, actually, so we can do calculation in a very geometrical way. So the answer is like this. We extend this boundary way towards the bulk. This is called surface gamma A. But there are many different extensions, so we have to choose one of them. And to choose that, we take a minimum area. We minimize the area. And then there is a unique one. And this minimization actually equivalent to solving Einstein equation. If we think this derivation of this formula. And then we take this minimal area surface and we calculate this area and divide it by 4g Newton. This is the same formula as the Beck-Einstein-Hawking formula. But difference is that this is not the horizon area, but the minimal surface area. And then this gives correct entanglement entropy in conformal field theory, which is equivalent to this ADS curve between A and B. So this is a holographic entanglement entropy, and this is a kind of generalization. You can think this is a huge, but it's generalization of black hole entropy formula. Because if we have some horizon, some black ADS, you can think about ADS black hole. The horizon is somewhere here. Then this gamma A also wraps on the horizon. So there is also contribution to this formula from black hole horizon. So that is really black hole entropy formula. So to have such a consistency, the coefficient should be 1 over 4g. But it's a very huge generalization because this is no longer horizon at all. And then also this, in the end, this gives the answer to this question, this basic question. And later, so this is owing to these people's excellent works. And this is now it's called entanglement wedge. Entanglement wedge means this information of region A. This is called, we can write this is a reduced density matrix or in a CFT side for A. So the information of this guy is actually can be reconstructed. It is hidden or stored here. This is a bulk gravity density matrix, reduced density matrix, which is included in an entanglement wedge A. Entanglement wedge A is like this region, right? This is surrounded by this minimum surface. And reduced density matrix in the bulk here is called problem. And these two are equivalent, basically. This is a entanglement wedge reconstruction. And that basically answers this question. So information here is encoded here, and the information here also encoded. So this is the basic formula which we can discuss about the quantum information in how quantum information related to gravity. And this is an intuitive understanding. So observer is here. So this is how also we originally formed this formula. So observer is sitting here, and the observer want to see inside this region B. So observer is a CFT lives on boundary, right? This is an ADS, inside is ADS. And the observer can only see A. And if we observer try to see B through ADS spacetime, there is actually obstruction, namely the horizon, black hole horizon here, and that surrounds region B, and so observer cannot see inside B. So then entanglement entropy should be related to this black hole entropy. Right? That's this area of gamma A divided by 4g. But there is many different choices of gamma A, right? So you can take this way or this way, and we want to optimize the result. That's the reason we minimize it. So this is roughly speaking how we can get this formula. There is a question: would it be possible to show the this one? Entanglement wedge is a volume of shaded. No. Entanglement wedge is just a region. Entanglement wedge is this region. We don't compute the volume or area, just a region. So, and more precisely, it's a density matrix, reduced density matrix in this region. This is an entanglement, basically, or this region itself, not the volume. Volume is related to something called complexity, but this is not the part of my. I don't cover that topic. Okay, so now I go to second version. It's just slightly generalized. This is a case with time dependence. This is a formula I find with Veronica Hubeni and Mukuro Rangamani. And this is actually time dependent case. So it's like inside the ADS, there is a non-trivial gravitational wave, for example. So always boundary is here. This is a boundary. And we take a t equals 0 slice. Boundary is fine. The boundary is just flat space, right? The ADS, inside ADS is some fluctuating, but the boundary of ADS is just flat space. We are constantly quantum field theory on flat space. So this is, we can take a nice canonical time slice, but then, and we calculate the entropy, but for static case, it's fine. Static case, I am implicitly take t equals 0 slice. And static case, you can just extend the boundary time slice to the bulk in a very trivial way. But here, it's no longer. So maybe you can take this time slice into this way, or maybe this way. There are infinitely many different ways because there is no symmetry inside. So, but nevertheless, we get a nice formula. We don't need to talk about any time slice. So only we take about time slice boundary, and this is region A, and the other region is region B. And then that defines CFT entropy SA. And how we can calculate it is just compute, this only depend on this boundary endpoints. And just connect these 2 points by geodesy equal minimal surface and extremal surface. So extremal surface means area is not minimized, but area functional takes variation. Stationary point. Area function is 0. Variation of area function is 0. This is extremal surface. And so it can, and this is time dependent. That means if you can compute same thing here, the surface is very non-trivial, and this area is different from this one. It has a time evolution, right? Entropy is now dependent on time, but we pick up extremal surface. And if there is sometimes, because this is a differential equation, if we solve this, there are sometimes 2 different solutions, maybe this surface or this surface, both are solution. In that case, we just choose minimum area one. So this is very important to satisfy basic property of entanglement. And if so, this is uniquely fixed and everything works well. This is a covariant time-dependent prescription of holographic entanglement. Okay. So, but anyway, so if we talk about this one, so we can show basic property of quantum entanglement. So this is called strong subjectivity. In my second lecture, actually this is plays a very important role also to derive basic property of quantum field theory. Strong subjectivity. And this is a very fundamental inequality known in quantum information theory. This is true for any quantum mechanics. Like there are 2 inequalities. SAB means this A union B. Right? So let's think this is an extra dimension Z, and compute SAB. SAB is this, AB is this region, right? So we take a minimal surface like this, which covers AB, and this length or surface area is SAB. And the BC is this B union C, so it's like this region, it's covered by this guy, right? It's covered by this guy, and it's this. Right. So yeah, B is this one, this area is this BC. But you can, with the same area, but you can put different color here and this here. This surface looks so strange, but this guy covers ABC. There is a smooth surface which covers ABC, which is minimum area, this green guy. And for this also, there is a nicer surface B. And then this inequality, like SAB is just this area, SB is this area, this inequality is obvious, right? So that way, this is basically triangle inequality in basic geometry. Tells us the strong subjectivity. And the other guy will just combine different ways, then this is also trivially true. So it looks trivial. Maybe from geometry, this looks very easy, but actually this is strong subjectivity. To prove this it takes up many calculation actually. There are many ways to solve this, but if we take a very complicated answer, you need many very complicated identities, maybe 4 or 5 pages you need to show this. Very complicated calculation. But in geometry, this is just one picture. You can easily find this proof. So that means algebraic property in quantum information theory. It's very quantum information theory has very complicated algebraic properties, but we can understand it very easily from geometrical picture. This is a really concept of programming, ADS-CFT plus one. Okay, and the other important point, so we can talk about general behavior of holographic entanglement. As I mentioned initially, so there is an areal divergence. This is an areal divergence. So you calculate this subsystem A, and with length is L. So you can imagine this is a subsystem A here, and calculate this gamma A, right? Area of gamma A. Area of gamma is divergent because metric at z equals 0, as mentioned, is divergent. Right? Metric looks like z square over dz square. Right? Metric looks like this, dt square and dx square. Right? So it's a metric divergent. So this around this region contributes is most. Divergent contributions should be proportional to the area. So this is looks like epsilon to d minus 1 and area of boundary wave. Boundary wave. This appears. This is reading. And there is also sub-reading divergence. This picks up some curvature of boundary wave. And there is and in the end finally end up with some constant in total dimensions, odd dimension. If total dimension is even dimension, logarithmic divergence. This is actually Euler normal, the conformal normal. It's central charge. But in an odd dimensional case, this is actually quantity called F quantity. F and central charge we often like to see is a very important quantity which characterizes the zero freedom of conformal field theory. And another important point is the monotonicity. Under renormalization group flow, and these F and C decreases under, always decreasing under algebra. At least this is true up to 4 dimension. And I will explain this kind of monotonicity in my second lecture. So I'm not talking. But it's like, anyway, using holography, at least this classical calculation compute all coefficients also in them, and then have this nice classification depending on even and odd dimension. Okay, so now go on. And another important known fact is Einstein equation. So of course, if we think quantum entanglement somehow describe gravity, then what about the Einstein equation? So Einstein equation should correspond to some dynamics of quantum entanglement. And we know at least some partial answer, the partial but very important answer to this question. So this is actually the Horning observation. So it's not so easy to go very nonlinear level, but if we talk about perturbative level or some some perturbative expansion, then so there is a basic rule of entanglement entropy. This is a kind of excitation. We put some gravitational waves. So we started the anti-Doshita space and put some small perturbation. And then that describes some excited state in common field theory. For small excitation, we know something called first law of entanglement entropy that basically says that growth of entanglement entropy is proportional to some excitation energy. Now this energy is more precisely called modular Hamiltonian, log of reduced-station matrix. And this change of this expectation value of energy, this modular energy, is just actually equal to the change of entropy. So this is analogous to first law of thermodynamics. We just take temperature to be 1. We just normalize to be 1. That is true. So, and delta S equal to delta H. And if we rewrite this in terms of gravity language, because we know entropy is area, right? Surface area in ADS. And energy also we can calculate by using holographic mapping, holographic energy stress tensor. And then in terms of holographic energy, we get this kind of differential equation. This entropy growth satisfies this kind of second order differential equation. This actually turns out to be Einstein equation. If there is a source, also the source term contributes. This is a matter story. We can actually have a perturbative version of Einstein equation from first law of entanglement entropy. And we can go also into these works. We can go further. Little first order correction, at least up to that one, this kind of relation with Einstein equation.
I have a question.
Yes, sure.
So why you can choose this temperature is a Hawking temperature?
No. This temperature, okay, good. So we take reduced density matrix, right? And this Hamiltonian is just minus HA. So this means, and if you know a usual canonical ensemble minus beta H, okay? So we take a beta to be 1 here because there are no coefficients here. That's the reason I said T equal 1. Okay?
If there is a black hole in the bulk,
so I'm not talking about any, okay, but I'm not talking about black hole at all. So there are no black hole in this geometry because it's just pure ADS. Just pure ADS and no black hole. And temperature is just very artificially introduced because separation maybe. It's unloop temperature.
What temperature?
Unloop.
Unloop temperature.
Unloop temperature. It's artificial. And just set to equal 1.
Okay.
So no black hole at all. Yeah, thank you for the question. Maybe there are other questions. Sorry, there are also other questions. Okay, so let me try to answer. How do we determine whether minimization done under Euclidean or okay, good question. This is a bit before, I think. So minimization is about the minimization. So that's a very important. So here we can take a minimization because we take a t equals 0. So everything is Euclidean, right? And actually ADS spacetime has a nice structure that metric squeeze, right, as z goes to the right. So I mean, in flat space, if we connect these 2 points, minimum length is just this coincide with the boundary. But in ADS, it should be non-trivial because large G has a smaller metric, smaller area is realized. But if we go too much, then it costs a lot of area. So there is a nice solution. But if we talk about this Lorentzian case, we cannot take a minimum area. That's true. So sorry, I didn't mention that. But if we go right direction, area equals 0, and that's trivial answer. That is not correct answer. So because of that, we take extremal surface instead of minimal surface. Okay, so that's the reason but finally, if we have several candidates, we can take minimum. That's no problem. And the second question, why is not L to this power? Okay, D minus 1. Okay, this one. This is area law. The divergence is area law. So, I mean, we talk about ADS D plus 1, right? D plus 2. Sorry, my combination D plus 2. And this is dual to CFT D plus 1. D plus 1 dimensional. And this boundary is D minus 1 dimension. Okay? So that's the reason we get this is the area, so D minus 1 and the epsilon. Okay. Okay. So now let me go. Good. This is a little bit sorry, this is somehow let's erase this. Okay, so this is a bit advanced topic, but it's actually useful for some black hole issue. But so okay, so this I talked about this formula, right? This is covariant entropy formula, extremization and minimization. But these are only true for 1 over G Newton, 3-level contribution. 3-level. I mean, Beck-Einstein-Hawking formula, 3 over the 4G Newton. But there is a next order. 1 loop collection gives order 1 collection. And a 2 loop collection is order G Newton contribution. So, but I'm talking about this classical contribution, classical general relativity contribution. But what about loop collection? Sometimes loop collection becomes important. This is 1 loop collection that is given by, and the full order actually answer is found by these people, Holkner, Lukowitz, Madison, and also finally the Engel, Halton on this quantum extremal surface formula. So minimization and extremization is very important to satisfy this strong subjectivity I mentioned. Minimization is important. But not only this 3-level contribution, but also we have the bulk entanglement. Bulk entanglement means this is the entanglement which I mentioned, this entanglement is inside, and this bulk entanglement inside and outside. This is a bulk entropy. And indeed, this bulk entropy is the entropy which was computed in this picture, cartoon. Sorry, this one. So this entanglement, I said it's UV divergent. This is like entanglement between A and B. This looks like a bulk field entanglement. This guy is exactly correspond to this part. This one, this part. So this entropy only that case only compute this part. That reason this doesn't precisely match with black hole entropy. Black hole entropy leading contribution come from this term. So that's the thing. But this part is very important. If we think of Hawking radiation and so on, black hole evaporation, this part is very important. That's I will come back later. Okay. So, and this is one more third formula. This is the third formula of holographic entanglement. Third version. This is the following question. So what about, what is the meaning of minimum area surface in Euclidean time-dependent ADS geometry? So I talked about Lorentzian time dependence here. Here we talked about the Lorentzian time. This is Lorentzian time dependent. But what about Euclidean? Maybe Euclidean time dependent maybe not so clear, but it's like appears in the tunneling effect. And also in ADS-FT, we often use Euclidean ADS geometry to calculate many things. And then Euclidean case has a very special feature. It's like there is a path integral, Euclidean path, path integral, and there is a final, future path integral and initial path integral. This gives two different quantum states. Euclidean good point of Euclidean path integral, it can create quantum states. If we want to prepare ground state, you have to path integral over a very long time. Right? You have to take beta goes to infinity. So if you take any quantum state, this goes to ground state. Right? And the Euclidean path integral useful to prepare quantum state, after Hawking state. And if we, but in the middle, so you can slightly perturb, right? Perturb. Then you get a different, ground state. The perturbed ground state, right here. And you can do other J and J prime, then you get a different quantum state. These two states are different. This is a, very different situation than Lorentzian time dependent. And this area safety compute just is overlap, inner product of two different states. You can calculate the inner product by from area safety to the Euclidean time dependent part. Accordingly, if you calculate minimal area, as I will explain maybe in the third lecture, this computes no longer entanglement, but other more generalized quantity called shield entropy. That's defined by somehow depend on two different states. I will explain the definition of this, but this is precisely agree with minimum area surface. Okay. And one more comment is that this is something called multi-entropy. So I'm probably not going to detail. This is a bit very advanced topic, but it's very current topic. And if we talk about ABC, so previously I talked about AB, right? Region A and region B. This area computes entanglement aspect. This area computes entanglement entropy. A is entanglement. But what about this? If we ABC tripartite system, maybe this length, this one, some of this band area are joining at some. This minimal surface is joined at one point, but maybe this sum of these three surfaces related to some interesting quantity. And the answer is at least partially yes, and this is called Baruch entropy. Baruch entropy is equal to the sum of this surface, and pointed out to these people. But sometimes this doesn't work. So this we have to be very careful. And so me and also our postdoc Jonathan Harper and our graduate student Tsuda worked out this two-dimensional calculation of this multi-entropy and found this kind of phase transition phenomena. This agree with holographic picture. So if A is very large, this surface is this kind of surface is favored, but if it becomes small, then kind of disconnected. And this is me, and we can confirm this to the CFT, and that somehow support this kind of formula. But what is the definition of multi-entropy, which is a bit complicated, so I'm not sorry. And this is one description for second lineage cases like this. And if you are familiar with replica toric, so usually replica toric, if we go around, so we have a second lineage entropy. If we go around this seat, it goes to here. But now we have a ABC, and if we go around this seat, this goes to here. and if you go under the other guy, it goes to the other state. So this is a kind of definition. But anyway, this is a very advanced topic. So if you are interested, please study this. But this measures some tripartite correlation. So entanglement entropy is bipartite correlation, but this is three-body kind of correlation related to this point. Okay, now I'm going to talk about two applications. So one is a black hole information. Oh, there is a question, sorry. And for the bulk entanglement is the leading order proportional to the area of bulk entanglement. I mean, this is not true. So, sorry, this is bulk entanglement. I think you're talking about this one. This is area of RT surface is this one, but this is completely different. That's the one comment. And does there exist in any first principle proof of holographic entanglement? Okay. So holographic entanglement entropy derivation of this assuming ADS-CFT was given by Lukowitz and Maldacena. Sorry, I shouldn't mention it. Please look at this paper. Okay, so any question also? Okay. Okay.
Yeah, I have a question about this pseudo entropy.
Okay.
I see this pseudo entropy means Bach is still ADS geometry.
Yes, exactly. Yeah. ADS,
So you just
asymptotically ADS.
Asymptotic ADS. So you just change time to the imaginary time.
That's right.
Then why it's so much different than the Lorentz?
Yeah. So but different
Here ADS geometry.
The two different states. Just two different states. Initial state and the final state. They are different. That's that.
So the Bach
anyway,
is still the Bach is okay. The physics is if I just the Bach remains asymptotic ADS.
That's right.
So is this two Euclidean and Lorentz are very trivially related, right? It's just
no.
weak rotation.
They are not. So if you just take naively Lorentzian geometry and take a weak rotation, you get a complex geometry. Metric becomes complex variable.
Okay.
Here
so
I'm
why?
talking about.
So
yes?
why we should worry about the Euclidean time? The Lorentz already tells us all the story. Is that right? Why did the Euclidean provide the new information?
Always Euclidean geometry is a fundamental thing. I mean, if you don't use Euclidean path integral, you can fix any quantum states. Even Lorentzian, we talk about Lorentzian holography, but there is a Euclidean, path integral is actually hidden there always to specify quantum states. To prepare quantum states, always Euclidean path integral is necessary.
Okay.
There is another question related, which is how is the ball entanglement entropy computed on the chat?
Yeah, I think I answered. Bulk entanglement, sorry, say it again. This bulk entanglement entropy, right? This is a quantum mechanical entropy between this outside and inside. It's nothing related to surface area. Okay, but anyway,
what's this? What's this EXT mean? Can you explain what EXT? That extent means extrema. I saw that the previous slide.
This one?
That this
EXT.
EXT.
So right. Extrema, right.
Extrema.
Okay.
And then minimize.
That's right.
Oh, okay.
Okay.
If sorry.
You have any, yes.
Yeah, I mean the bulk entanglement entropy is just the von Neumann entropy in QFT.
That's right.
Here.
That's right.
Yeah. For the QFT, there is a array law. Yeah.
Okay, yeah, that's area law. Yeah.
Yeah, I mean, if we think the area law allows this bulk entanglement entropy, the boundary of the MA is just the RT surface, so the leading term of this term is proportional to the area of
okay,
the RT surface.
I think, yeah, okay, good point. Yeah, that's true also, that's true. But I'm area law, but there are also other contribution. Of course, area law contribution, but there are many finite contributions. There are many non-local contributions and so on. But it is true. So leading divergence is area law. That's the same as this area. Okay, that's true. That's true. Okay.
Okay, thanks.
So that actually changes gives a renormalization of Newton constant. Actually, only changes the coefficient.
This formula I worried is because matter also coupled to the gravity. Why they are separate? Because matter coupled to the gravity is only mixed in turn because matter.
Mix, yeah. Of course, matter back reacts. So quantum mechanical, for example, effect, right? Quantum mechanical energy stress tensor of matter back reacts to the geometry. That is true. So this is after back reaction, we just calculate this area.
After the back reaction.
And you are right. Yeah, it's very complicated calculation.
Okay.
Okay. But anyway, for pseudo entropy, any other question, please ask in my final lecture, third lecture next week. I'm mainly to focus on this. Okay. So now let me go on. So I'd like to talk about black hole. I want to talk two things, but anyway. Yeah. So this is a black hole information paradox. So this I mean, black hole has an entropy that is itself fine, but problem is that so after Hawking radiation, black hole has a temperature, and so it radiates, right, and evaporates. And so inside the black hole, there are a lot of information is stored, but it's gone after time evolution, after evaporation. So inside the information, that means somehow this contradicts with the unitarity of quantum mechanics. In other words, if we assume original star system is a pure state, and at time evolution, everything should be pure, but finally only end up with radiation, looks like a mixed state. Right? That's a contradiction. Pure state always evolved into pure state under unitary evolution. So is it really quantum mechanics is unitary or not? So Hawking raised this paradox. Maybe in gravity, quantum mechanics is somehow unitary. Maybe unitarity in quantum mechanics might be lost. But actually, ADS-CFT tells us that this is not true. So ADS-CFT argues that gravity, maybe gravitational dynamics is not so easy to understand, but it's equivalent to some conformal field theory or some just quantum many-model system that is obviously unitary. So that means there should not be any problem about unitarity. But the next question, how we can really resolve, how we can extract information from radiation. This is this question was, becomes sharp if we think about something called page curve. Don Page proposed this curve. So we model black hole radiation, like we have a black hole Hilbert space and radiation Hilbert space tensor product. And we start with always some quantum state. This maybe start from some pure state after gravitational collapse and some time evolution, unitary time evolution. And we talk about the entanglement between radiation and black hole, and this reduced density matrix for radiation. And we calculate the entropy for radiation, rho log rho. And if everything at total state is pure, then it should go this way, this kind of red curve. So we have a black hole is very large and emits small amount of radiation. So entanglement should be very small, right? Because radiation is very small. But if radiation grows larger, then entanglement entropy growing. But when black hole degree of freedom and radiation degree of freedom is the same order, then this is a maximum. But after that, radiation gets larger, but black hole is very small, right? So there are not so many entanglement between them, right? Small number of qubits here. So it goes to 0 in the end. And when evaporated, then black hole disappears, so that we know radiation don't have any pair, right? Any partner which their radiation can entangle with. So that means it goes to 0. So this is called page curve. But naive calculation of Hawking radiation in quantum field theory, it's always radiating, so entropy is growing always. So there is an order 1, this kind of difference. This means that this label in the end up with mixed state, but this ends up with pure state. This is a very sharp difference. And anyway, good thing here is that we can calculate this explicit quantity rather than asking very philosophical question or abstract question. So we just compute this radiation entanglement and see which is true, right? And this is actually recent.
I'm sorry.
Yes,
I don't understand this. Can I look at this
Mm.
Hamiltonian? You know, you
Mm.
evolve the unit state. This
Mm.
Hamiltonian is the whole Hamiltonian of the black plus radiation.
That's right.
What's
that's
the
right.
the whole system's Hamiltonian?
Full system, that's right.
Black hole plus radiation.
Plus black hole plus radiation, of course.
The total Hamiltonian.
That's right.
Do we know this Hamiltonian?
Yeah, it's not, in simple model, we can have some 2D gravity. People, compute this by using partial integral formalism, especially. Well, as we will explain, so also ADS-CFT computes as a geometry. Right? The ADS-CFT time evolution is just described by this, the evolution of ADS space-time, right? So that implicitly we can compute this effect of time evolution.
You mean for 2D, people know higher dimension?
Especially without using ADS-CFT, people can compute time evolution of quantum states, maybe running time of. Okay, so yeah, so this is a very interesting recent development, but already maybe 5 years ago. This is made by this Pennington and Almeheri and collaborators. And this is a discovery of island formula. This formula, you might think something similar to this one. Right? This is basically generalization of this formula. Generalization of this somehow it leads to this formula. This is an island formula. The island formula tells the following thing. So new thing is not only we consider matter. So we just talk about the entanglement entropy for some matter, with some region A, usually SA. And maybe sometime we can apply holography, but no, let's assume we don't apply holography at this point. But the new thing is that matter is interacting with gravitational part. Gravity includes black hole horizon, somehow black hole, and interacting these two guys with each other. Then, if you want to calculate the entanglement entropy for region A, it's very tricky because there is a gravity. That's the island formula. The correct calculation of entanglement entropy for this region should be taken into account some contribution called island. Island is this yellow part. Boundary is the red guy. This yellow part. This island typically lives inside the black hole. If there is no black hole, island should not appear. But if there is a black hole, this island appears. And initially, you can take the sigma island to be orbitally shaped. Let's assume one fixed shape of sigma, and we calculate this guy. Area of this boundary of sigma, which is this because this is a gravity, so there is a gravity entropy, gravitational entropy, analogous to vacation Hawking entropy, but this is not black hole. And next thing we calculate this, we combine this subsystem A with island. We regard A and sigma as the same side, and the outside is different. So we compute A union sigma, and this is a bulk entropy. This is a three-level entropy, gravity entropy, and we take a sum of this and minimize over all choice of sigma. Sometimes maybe if sigma shrinks to 0 size, that means there are no island. But if sigma has some finite size, there is some island configuration in favor. So this is the island formula. This is basically you can derive this formula by somehow thinking about generalizing this formula. This form, because it's basically the same form. And so this formula works very well because initially, nothing happened. Like there is a small radiation, but if you add the iron, this doesn't change anything. So iron should not appear. But if we go to later time, so Hawking pair is created quite a lot. Right? So we have a lot of Hawking pairs. So Hawking pair is here, and Hawking pair is there, entangled each other. There are many such pairs here and here. So there entanglement entropy between A and outside is very, very large. But if you combine this sigma with A, then you can reduce entanglement entropy because they've canceled, right? So that way, that's the reason we get island and entropy goes to zero. So using this formula, this formula can be also derived in 2D gravity without using holography. But the other way we can use this holographic entropy formula. Originally, this was formed by applied holographic entanglement, but also we can derive this in other way. But anyway, so by using that, we can realize this page count. So this is a very interesting thing. And this also tells us, for example, because we know this entanglement wedge-like idea. So at later time, observer who are only accessible to A actually also accessible to sigma inside the black hole. Inside the black hole looks like far from the observer, right? Cannot follow, but actually that part can be visible from this observer through the Hawking radiation, because this entanglement wedge also covers this region. This low A covers this sigma region. So that's the reason. So that's the way. So we can resolve. At least intuitively, we can resolve black hole information paradox. So from the radiation, we can get the information inside the black hole. So inside the black hole don't disappear, but actually come out into this Hawking radiation. This is a modern understanding of this black hole information paradox. There is we don't have any access to inside the black hole. Then how will calculate the area of island? Sorry, this case is okay. These are just quantum field theory calculation. Anyway, observer don't. I don't mean observer calculate the area, but in this calculation, we just calculate the area by this using this quantum field theory model. But observer actually, maybe if we really wanted to experiment how experimentally measure, but there is radiation right come out of this. And from radiation, if we look very closely of this non-trivial correlation of radiations, you could see information of this region inside the island region. But this is very, quite complicated task. But nowadays there are, we know in principle how we can extract some information in simple models. But it's actually one comment is that this is the interesting thing is that black hole information paradox, of course, we usually say inside black holes cannot be seen. That is actually true. So to extract information inside the black hole, maybe you might think some experimental kind of equipment, but even if you have quantum computer, current understanding tells us it's impossible to get the information. But if we have some, quantum system which go beyond quantum computer, maybe it is possible. This is something called complexity theory. So in principle, you can extract information, but in usual available experimental devices probably not possible. This is I think current understanding. So that actually avoids this contradiction of the usual ideas. So black hole information paradox looks paradox, but because if you are really looking at the theoretical thing, it's not paradox. But if we want to really need some equipment, then it's really impossible to get inside the black hole. So this is a very interesting. So there are no mathematical contradiction, but that's the reason originally Hawking says that this is a paradox. But it's not. Both are, in some sense, both are correct, but there are no paradoxes. Okay, but this is something I wanted to mention here. But anyway, so if we this is something I'll explain in my next lecture. So in higher dimensional language, well, if we put some more holography, you can extract information from island through some wormhole from observer. This is another idea, but I will probably explain this later. I postpone question later. Okay. So let me quickly mention my final topic. This is the emergence of universe. So this is also the title of my this lecture. So how we can understand the emergent universe from quantum entanglement. This holographic entanglement entropy suggests that there is a 1 qubit of quantum entanglement for each Planck length area. So you can rewrite this formula in terms of Planck length. So Newton constant is just Planck length some power, d minus 1. So area divided by Planck unit cell, right? So for Planck unit cell, this is a Planck unit cell, 1 Planck unit cell, this is LP Planck length. We get a 1 qubit, one bit, one bell pair, 1 entanglement qubit. like this. You can divide it to small cell, and for just 1 square centimeter, you get 10 to the 65 qubit. This is very amazing now. And so that suggests that space-time may emerge from entangled qubits, because you can A and B are artificially chosen. So A is nothing related to black hole. It's just choose any point, any region. So this surface is just artificial. You can choose other A, like here, then you get another surface and a lot of qubits there. So if in that way you can choose any points of A, then that means these qubits are everywhere in the space-time. So and from this quite a lot of somehow arrays of this, I mean, qubits, maybe you can calculate this area as a number of entangled pair. So, but this looks very heuristical, but maybe just philosophical, but actually there is a way to get this kind of explicit realization in some concrete model. This is a nice model called tensor network. Tensor network is some graphical description of quantum states, and it describes some network quantum entanglement. This is originally used to do some, and also applied many also recently to some condensed matter system, to understand some complicated condensed matter system by using numerical calculation. There is a very powerful tool. This is called tensor networks. And in conformal field theory, there is a mirror tensor network proposed by Budar. This kind of very nice structure of tensor network is known. So this looks like anti-digital space. This is the point. So there is a many spins, and the idea is to, if we go this way, we coarse-grained spin. So spin combined into one, but at the same time, we should cut quantum entanglement by unitaries. But from opposite side, we start with just single spin, but divide it into 2 spins and put some entanglement and divide it into 4 spins, and you can somehow get the emergent space from, if we look this way. So you can add some entanglement, and that increases the size of the universe. And if we calculate the entanglement entropy for A, then basically entanglement is just counting number of links, because each link add entanglement. So, and if we have a region A here, but you might count number of spins like this way, but this is overcounting, right? So many overcounting, and we have to minimize to get the optimized result. This is very similar to holographic entanglement that gives minimal area size. And also there are other versions called happy model or random tensor network model, which is based on this quantum error correcting code. But they also have a slightly better property that it's precisely this number of count, number of bonds gives number of links, intersecting links, precisely gives the entanglement. Here it's a kind of approach. So these are very discrete models. What about quantum field theory? So this is actually our path integral optimization. This is my very finite topic. This is my work with Kaputa and Kundu and Miyaji and Watanabe. And so can we describe this quantum field theory as a tensor network? So actually, best idea is to use a path integral. This is now Euclidean path integral. We have in mind some path integral like this. And the point is that we discretize it. So this, as I mentioned, the Euclidean path integral gives ground state, right? Beta h, for any state means any boundary condition here, and beta goes to infinity, you can get a ground state. So we can do this path integral, and if we do this in a lattice calculation, lattice discretization calculation, regularization calculation. So you can divide into many cells. But actually, initial path integral is not important because you can omit it, because this is for a long time we do path integrals and then project it down to ground state. Initially, we can coarse grain and gradually fine grain. And finally, it should be very fine grain. And this tensor network looks very similar to this one, this kind of hyperbolic tiling. This is the same as this guy and this guy, Merame. And indeed, this actually gives the correct answer. And this explains the time slice of anti-digital space emerging. This is the most efficient way to do some numerical calculation, and that is exactly given by ADS-CFT correspondence. You can make this more precise. So this is a heuristic picture. We are talking about some kind of cells, but we can put some rule. One cell have a unit area, one cell. Then this looks like curved space-time, right? This is one area, this metric is very large, but very small here. So this looks like hyperbolic space. So we can have use metric and use this rule that for one unit area cell, we have one bracket like this. So that then this this kind of tiling, right? Tiling is written in terms of this Weyl factor of metric. And this Weyl scaling, and this is conformal field theory, so wave function is proportional to each other. It doesn't change. This is still conformal invariant. So only normalization of wave functional changes. And this wave functional normalization is turned in 2D CFT. This is well known to be just actually Liouville action. Liouville action is taking very beautiful action like this. And the idea is we want to do some most efficient calculation. So we want to minimize this quantity. This is something, same thing like complexity. And this minimization of Liouville series is well known. We get the anti-De Sitter method. So that way, most efficient calculation prefers anti-De Sitter discretization, anti-De Sitter space structure. And this is also very similar. Mirror network also very efficient because in the end, we get the ADS. And if we have put some excitation somewhere, then you want to keep this information, then you need to do some fine graining. So that means that changes the metric, right? So and indeed, if you put some particles, so it changes the metric, right? And this adds general relativity. So this kind of, very information theoretical approach, like we just minimize cost of information as a computational cost. That actually also leads to, at least qualitatively leads to this Einstein equation. And we can also go further. This is more later work with Brosh and Kapta and Ge a few years ago. So we can show that we can embed this formalism into real holographic calculation, and we can say this path integral optimization, this most efficient calculation, is equivalent to maximization of Hartree-Hawking wave function for ADS universe. So maybe this suggests that maybe gravity, of course, most probabilities, so probability or universe which realizes in gravity is measured by the Hartree-Hawking wave function. So maximization Hartree-Hawking wave function is very natural. And that seems to be related to this computational cost efficiency. So that there is some, maybe gravity might be somehow related to some ideal quantum computer. This is very interesting thing. And okay, so this, yeah. And but this is, so far I'm mostly talk about anti-De Sitter space, right? But what about our current universe, namely De Sitter space with positive cosmological constant? We know observationally our universe probably have a positive cosmological constant, or De Sitter space is very important in the context of inflation. So more realistic universe, how we can understand? This is non-trivial, very difficult because we have to have an emergent time direction. But there is some interesting progress, and which I will explain in my final lecture. Okay, so basically these are all of my lecture today. And here is some sketch. I talked about this usual physics. We talk about this in matter. And so if we look into, if we use accelerator or microscope, we get to some elementary particles. And from elementary many particles, we get some emergent non-trivial physics like superconductor or topological insulator and so on. Many nice emergence of condensed matter physics. But now we have some nice relation between entropy and area. Entropy's information is somehow related to area geometry. So then we can have also a very interesting new direction of physics coming up. So universe, we talk about universe, and if we magnify universe by microscope by using holography, we get a collection of qubits. And also from collection of qubits, universe emerges. And this is a good approach of quantum gravity. And if we go opposite way, then this suggests that maybe gravity is the fastest quantum computer. This is actually, this kind of topic is very hot in the context of compute. Quantum computing computer if we have a larger system, but they do calculation of entanglement, just area. So why it is possible? It looks contradictory in assuming some consensus of in quantum computing theory. So it's quite a hot topic. But also for quantum gravity approach, we can discuss this emergence. And here are some lists of future problems. And I'm not going to detail, but obviously the digital space is very important to understand from the viewpoint of holography. Maybe so time coordinates seem to emerge from some sort of entanglement, more precisely just pursued entropy, which I'll explain in my talk. And yeah, so entanglement, we talk about the on the minimal surface, but what about the internal space? In ADS-FT, we have an ADS space times some sphere or some internal space. What the connection, geometrical connection to entanglement entropy? I just started to explore, so maybe it's quite interesting. And maybe, yeah, ADS-FT is still not completely proven, so maybe quantum information approach is useful. And we want to understand this black hole entropy formula. It's directly from quantum gravity. So far, using programming to understand for entropy, famous story of Strominger microscopic explanation of supersymmetric black hole. This is also using holography. But what about quantum gravity? This is still not completely understood. And this is another direction, but it's also interesting to talk about some experiment, really condensed matter experiment, but the tabletop experiment like cold atom system, ion trap, and to simulate holographic spectrum, space-time, and see some quantum information nature. This is also quite interesting topics and recently getting hot in that community. And of course, finally, we want to understand quantum gravity explanation of this, how this universe is created. Okay, these are all of my talks. Thank you very much.